Hello and welcome. In this video, we're going to talk about how to complete the square, how to use completing the square to solve a quadratic, how to use completing the square to write a function in vertex form, and then we're going to wrap up by looking at a word problem and how completing the square can help us solve a quadratic word problem, similar to some of the ones we've solved in previous videos. So let's go ahead and jump right in. So up until this point, we have talked about how to solve quadratics by factoring, and we have talked about how to solve quadratics by graphing, never really the optimal choice there. And we have talked about how to solve quadratics using the square root method. And the nice thing about the square root method is that really it's just like solving for x. It goes back to some Algebra 1 skills. The problem with that method is that not every problem can be solved using square roots, just like not every problem can be solved using graphing, just like not every problem can be solved using factoring. If something doesn't factor, if it's not easy to identify the intercepts from a graph, then we don't really have a solution that we can identify using those methods. This is why we need more methods. So today we're going to talk about completing the square, and in the next video we're going to talk about the quadratic formula. The idea in this video is if we could identify a perfect square trinomial, like this would factor to be x minus 8 quantity squared, and we could factor that perfect square trinomial, right? This factors to be x minus 8 times x minus 8 equals 100, and that's why we could write it as x minus 8 quantity squared. Now at this step here, we're actually ready to solve using the square root method. So completing the square is sort of a middle step to allow us to solve using square roots. So from here, we could square root both sides. The square root of x minus 8 squared is just going to be x minus 8. The square root of 100 is going to be plus or minus 10. So x minus 8 is negative 10, and x minus 8 is positive 10. And then we can add 8 on both sides to get negative 2 and positive 18. Now, if we look at the next problem and recognize that this is also a perfect square trinomial, 225 is a perfect square. The square root of 225 is 15, and 15 plus 15 is 30. Then we can rewrite this like this, which means we can then take the square root of both sides. This is going to give me x plus 15 is plus or minus 11. So x plus 15 is negative 11, or x plus 15 is 11. That's going to give me negative 26 and negative 4. So one thing I want to point out here, we did not solve by factoring. Even though we did factor, solving by factoring means that this is equal to 0, and we're factoring the left-hand side so that we can use the zero product property. We did not use the zero product property. We identified a perfect square and factored that so that we could square root both sides. So this method is different than the factoring method. It's okay for our quadratic to not be equal to 0. We want it to be equal to something that we can factor to be something squared. Now, both of these problems worked out really nicely because they were perfect square trinomials on the left-hand side. But what happens if they're not perfect square trinomials on the left-hand side? Is there a way that we could manipulate what we have on one side of the equation in order to be able to factor it so that we can use this method? That's what we're going to be exploring in our next few examples. So before we jump into equations and solving, I really want to focus on this idea of creating that perfect square trinomial. So again, in those first two examples, we already had a perfect square trinomial and we could factor that. But if we don't already have a perfect square trinomial, how can we create one? That's what we're going to focus on here. So there's no equal signs, there's no equation. Our goal right now is just to be able to say, what number, how could I figure out what number needs to go in this C spot so that I could factor to have something squared? So in order to have something squared, I don't want to just think about what we need here. We need to have two sets of parentheses that are exactly the same, because if I have two sets of parentheses that are exactly the same, I can write that as one quantity being squared. So let's just think about this in terms of factoring. If I factored x squared, that would give me x times x. That's how I could get to x squared. And I know that these two numbers are going to multiply to be c, but I also need them to add to be negative 14. So how is that going to work? If I want these two sets of parentheses to be identical, but I want 14 to be what I get when I add them, that's going to mean that I need x plus 7, because 7 plus 7 is 14. That means if I multiplied this out, I would end up with x squared plus 7x plus 7x, or plus 14x plus 49. So the number that I need to go in this C spot is 49, because that's what I would get if I expanded this polynomial out. And what I would have after I added that 49 is the ability to factor this to be x plus 7 quantity squared. And this will allow me to now solve using the square root method, to square root both sides and to isolate my x. So the key thing that I want you to be thinking about is we're taking that middle number, and we're really just, there's sort of a formula for it. We're cutting it in half, and we're squaring it. So looking back at 14, we said, I need these to be identical, and I need these two numbers in purple to add to be my middle number. So I'm just going to cut that number in half. 7 and 7 adds to be 14. That's where this 7 inside my factored form comes from. In order to do that, we have to consider that we would multiply all of this out. And if we multiplied all of this out, we would have a 49 over here. And that's why we would have to put a 49 in the spot where C is. So we're going to use that same logic on this next question. So I'm going to ask myself, I need two sets of parentheses. I need them to be exactly the same so that I can factor them to be something squared. So what makes x squared? Still, I'm going to have just x times x. Then I'm looking for something that is going to add to be 40, but I need these two sets of parentheses to be the same. So if I want them to be the same, I'm going to divide 40 by 2. That's going to give me 20 and 20. So the factored form here is going to be x plus 20 quantity squared. But if I expanded, if I multiplied these two sets of parentheses out, I would get x squared plus 20x plus 20x plus 20 times 20, which is 400. So the number that I would need to be in this C spot would be 400. So if this said x squared plus 40x plus 400, I could factor that to be x plus 20 quantity squared. Now, I've been showing this with those two sets of parentheses, and that's a great way to approach doing this. Some people really just like to use the shortcut, so they just identify what is this b value. B is 40. What are we going to do? We're going to take half of 40, and then we're going to square it. That's going to give us 20 squared, so that's where our 20 comes in. That's going to give us 400. It's really how you show the work off to the side that helps you complete the square. Either way is fine with me. I don't mind if you're showing the factoring steps. I think it helps your brain really process what you're doing. And then eventually you may be able to skip that step to become a little bit more efficient. So let's add in some equations here. We just factored some expressions, or we identified what we would need to do to factor some expressions. Let's actually apply this to an equation like we've been looking at in the rest of the chapter. Okay, so the first thing that I want to point out that's different is that we have three terms here. We don't have a C value. In this case, we have plus 7. This is an equation, which I can see because it's equal to 0. And this right here is not a perfect square trinomial. I need a different number in the spot where this 7 is so that I can factor this to be something squared. So I'm just actually going to move the 7 to the other side. So I'm going to subtract 7 on both sides so that I can focus on completing the square without that 7 being there. So again, my goal is to be able to write this as two sets of identical parentheses so that I can factor this to be something squared. What makes x squared? Well, that's x times x. I want something that is going to add to be negative 10, but is also going to be identical. So half of 10 is 5. So this is going to become x minus 5 quantity squared. Now, in order to have a minus 5 here, what I'm doing really, if I expanded this out, is I'm multiplying these two 5s to get 25. So this is going to be plus 25. Now, here's the big difference. I can't just add 25 to the left-hand side of the equation. I have to keep things balanced. And if I added 25 to the left-hand side, now this is increasing one side but not the other. So to balance that out, I need to add 25 over here because now I'm changing the both sides of the equation in the exact same way. I can simplify 25 and negative 7 to get 18. And now I'm in this factored form so I can solve using square roots. So again, to recap, I'm figuring out what number I need to add to both sides so that I can complete the square. That number comes from taking half of our b value and then squaring it. So half of 10 is negative 5. Negative 5 squared is 25. That's where we figured out what this number is going to be. Now we can solve the equation that's left by square rooting both sides. This is going to give me x minus 5 equals plus or minus the square root of 18. I'm going to add 5 to the other side, and then I'm going to simplify the square root of 18. Square root of 18 is 9 times 2. The square root of 9 is 3. And then I'm going to put set notation around my answer. So again, the first thing I'm going to do on number 6, so that I can focus on completing the square, is move this 5 to the other side. I'm going to figure out what number I need to have in my parentheses so that I can rewrite this as something squared. Well, I know that x squared is x times x. I want to take half of 18, so that's going to give me negative 9. And then if I expanded this out, I want to square that 9. That's going to give me 81. And I'm going to add 81 on both sides. Now, if we look back up, this is a perfect square trinomial. It does factor to be this. So it's nice that we can check what we're doing as we go. So this is going to give us x minus 9 quantity squared equals 76. We can square root both sides. So that's going to give us x minus 9 is plus or minus 76 is 4 times 19, and the square root of 4 is 2, so 2 square root 19, and then I'm going to add 9 on both sides. And remember, when you're simplifying those radicals, remember that you can, not 19 though, make your upside down birthday cake and figure out how exactly we are simplifying that radical. Okay, so something I want to point out is that all the examples we've done so far have just had x squared as our first term. What happens if there is a different number in front of x squared? What happens if there's a 2 there or a 7 there? How do we work with completing the square when we don't have an a value, that ax squared value, when a isn't 1? Okay, so for these next two examples, our a value, right, if we're thinking about ax squared plus bx plus c equals 0, our a value is not equal to 1. So when we complete the square, we have to keep in mind that we want 3x squared as our end result when we expand everything out in our polynomial. So we're going to start the same way by moving the constant that we don't want to worry about to complete the square to the other side. But then it's going to be much easier to complete the square if there's not a 3 in front. So what we're going to do is we're actually going to factor out that 3. So if I factor 3 out on the left-hand side, what would be left inside parentheses would be x squared plus 2x, because I'm just factoring the 3 out of these two terms. So that now I can complete the square with just this piece here. So using the same logic that we've been doing, our ultimate goal is to get something squared. The something that's going to be squared is x plus half of that middle number, so x plus 1. And if I squared 1, that c value would be 1. So now what I want you to think about just briefly is if I put a 1 here, what happens when I distribute this 3? So I'm actually off to the side just so that you can see why this happens. If I distributed that 3, I would get 3x squared plus 6x plus 3. And on the right-hand side, I would still have 4. So I want you to ask yourself, what's different from this step, the first step that I wrote, and this step right here? It's not that I just added 1, it's that I added 3 times this one. So I have changed this equation by adding 3, which means instead of adding 1 to both sides, I actually need to add 3 to both sides. So you can think about it as though if we distributed this 3 and multiplied it by that 1, we're going to actually add 3 to both sides. So I'm still going to have the 3 in front of my parentheses, and then on the right-hand side, 4 plus 3 is going to give me 7. And now we can solve. So we're going to divide both sides by 3, so x plus 1 squared equals 7 over 3. Then we can take the square root of both sides, so x plus 1 equals plus or minus the square root of 7 over the square root of 3. And then subtract 1, so x equals negative 1 plus or minus the square root of 7 over the square root of 3. Now, something that you should have learned in Algebra 1 or geometry is that we actually don't leave radicals in the denominator of a fraction. It's just bad notation. The solution to that is just something that we call rationalizing the denominator. And all that means is we don't want radicals in the denominator. So if you're going to have one, you're going to multiply by what you see in that radical. Again, this is called rationalizing the denominator. Because what happens when we do that is in the numerator, the 7 and 3 are both inside the same radical. So that's going to become the square root of 21. In the denominator, the root 3 times root 3 is going to become root 9, and root 9 is just the same thing as 3. So it's always going to end up just being that number that's left inside. So this is the square root of 21 over 3. So our final answer, x equals negative 1 plus or minus the square root of 21 over 3. All right, same process for number 8. So the first thing I'm going to do is move my 5 to the other side, so subtract 5 on both sides. Then on the left-hand side, I'm going to factor the 2 out so that I can focus on completing the square with what's left. My ultimate goal is to get, and again, my 2 will just come down, x plus something squared that would make me be able to factor here. So x plus half of 4 is 2, and if I squared 2, I would get 4. And then let's see how that is changing this equation. Well, if I was to distribute this 2 out, I would actually be changing this equation by 2 times 4 or by 8. So I'm going to add 8 on both sides. So this is 2 times x plus 2 quantity squared equals negative 5 plus 8 is 3. I'm going to divide both sides by 2. So x plus 2 quantity squared is 3 over 2. Go ahead and pause the video and see if you can work through the rest of the solving part of this on your own and see if you can rationalize the denominator on your own. All right, hopefully you had time to work through that. X plus 2 is going to be plus or minus the square root of 3 over the square root of 2, which I know I'm going to need to rationalize. So I'm going to multiply by the radical in that denominator. I'm also going to subtract 2 on both sides, so negative 2 plus or minus the square root of 3 times the square root of 2 is going to give me the square root of 6. The square root of 2 times the square root of 2 is going to give me the square root of 4, which is 2. So now we know how to complete the square really in any situation. And I will say that that's not always the best way to approach a problem. That's why we're going to learn the quadratic formula in the next lesson. But completing the square actually allows us to go back and do something that we learned how to do in chapter 2 in a more efficient way. And that's going to be to write our quadratic function in vertex form. So we're going to look at that next. So in chapter 2, we learned that we could find the vertex of a quadratic by taking the opposite of b over 2a. That's going to give us our axis of symmetry. X equals the opposite of b over 2a. And then we could plug that in to find the vertex. And then after we had the vertex, we could plug in any other point so that we could write it in vertex form. And vertex form is super helpful because it helps us identify transformations. It makes it easier to graph. It helps us be able to see what our vertex is. And the vertex has a lot of information about increasing, decreasing, maximum or minimum value, and so forth. So having something written in vertex form is really helpful. And having a more efficient way to write something in vertex form is going to be helpful as well. So we are talking about the function y now. So instead of moving 18 to the other side, it doesn't really make sense to talk about it on the other side. What I'm actually going to do is I'm just going to move it over. I'm going to sort of ignore it temporarily. I'm going to have it written there, but I'm going to ignore it. I'm going to complete the square with what I can see inside my green parentheses. So I'm looking at 12, negative 12. Half of 12 is going to give me 6. So inside parentheses, I'm going to have x minus 6 quantity squared. If I squared that 6, I'm going to get 36. And normally we would just add 36 to the other side of the equation. But again, this is a function, so the name of the function is on the left. It doesn't really make sense to add 36 on both sides, and then that actually makes it take a whole step longer to have something be in vertex form. The reason we normally would add 36 on both sides is to keep our equation balanced. But there's another way to keep it balanced. If I add 36 on the right-hand side of the equation, but I also subtract 36 on the right-hand side of the equation, if you look at my green numbers, I haven't changed the equation at all. I may have added 36, but I also subtracted 36, which when I add those together gives me 0. So I haven't changed the equation. I've just changed the way that it looks to benefit me. So now if I combine like terms on the outside here, 18 and negative 36 is going to give me negative 18. And now I have a quadratic that's in vertex form, which means I can immediately identify the vertex as the opposite of what I see inside with x, or the h value, comma k, the outside part, the vertical translation. So I'm going to encourage you to pause the video on number 10 and try and work through it on your own, and then unpause the video and see how you did. So first, I'm going to move my 16 over. I'm going to figure out what I need to do to complete the square with this x squared minus 22x. Well, half of 22 is 11. So I'm going to have x minus 11 squared. If I square 11, I get 121. So I'm going to add 121 on the inside so that I can complete the square. And I'm going to subtract 121 on the outside to keep my equation balanced. 16 minus 121 is 105. So now I have my quadratic written in vertex form, and I can identify the vertex as 11, negative 105. So being able to write the equation in vertex form in this way is a little bit more efficient. Okay, the very last thing we're going to look at in this video is how to extend this to some word problems. All right, answer the questions by rewriting the function in vertex form. So the directions are specifically telling us to write the function in vertex form. There may be other ways to go about doing a problem like this, but we need to start by writing our function in vertex form. You and your friend meet at the park to play home run derby. The path of your longest hit can be modeled by this function, where f is the height in feet and t is the time in seconds after the ball is hit. Find the maximum height of your hit, that's part A, and then how long does it take the ball to hit the ground, that's part B. So before I even really get into this, I want to identify what we're being asked for. The maximum height, we know from previous chapters, is asking us about the y value of the vertex. How long does it take to hit the ground is asking us to look at when the height of the ball is 0, meaning what values of x or t in this case would make the height, or f of t, equal 0. So the very first thing we're being told we need to do is write it in vertex form. Well, in order to write this in vertex form, I need to factor out that a value. So I'm going to take 16t squared. I'm going to factor out negative 16. I'm going to leave my 3 off to the side, just like I did when I wrote the last two problems in vertex form. If I divide 96 by negative 16, I'm going to get negative 6. And then I'm going to complete my square. So half of 6 is 3. So this is going to become t minus 3 squared. And if I square 3, I'm going to get 9. To keep my equation balanced, I need to remember that I'm multiplying negative 16 by that 9, which is negative 144. So to keep that balanced, out here I need to add 144. That's going to give me plus 147. So now that this is written in vertex form, we can identify the vertex and the y value. So the vertex is just 147, which means the maximum height of the ball is going to be the y value of the vertex. So the maximum height is 147 feet. Question 2 says, how long does it take for the ball to hit the ground? So we said that is really just asking us, when does our function that we just rewrote in vertex form, when does that equal 0? So let's use the fact that we wrote it in vertex form to solve for t. So I'm going to cross off this in the middle. We're just going to look at 0 equals this. So I'm going to subtract 147 on both sides. I'm going to divide by negative 16, which is going to just give me positive 147 over 16 equals t minus 3 squared. And then I'm going to solve using square root. So I'm going to square root both sides. That's going to give me plus or minus the square root of 147. The square root of 16 is 4. And that's going to equal t minus 3. So t is going to be 3 plus or minus the square root of 147 over 4. Now, it doesn't make sense for this to be both positive and negative. We're asking how long does it take. So how long it takes is going to be the positive version of this answer, which is going to be t equals 3 plus the square root of 147 over 4. Now, in a real world situation, we would grab a calculator and figure out what this is. But since you're not going to have a calculator on this assessment, I just want you to practice writing your sentence with this exact answer. As ugly as it may look, it will take 3 plus the square root of 147 over 4 seconds to hit the ground. All right, we're going to look at one more example, one more word problem. When your friend hits the ball, his path, or the path of the ball, can be modeled by the equation g of t equals negative 16t squared plus 80t plus 4, where again we're talking about height and in feet and time in seconds. And we're going to do the same thing. Find the maximum height of your friend's hit and find how long it takes to hit the ground. So I actually encourage you, use the last problem as a sample and see if you can work through this problem on your own, and then unpause the video and see how you did. Now, something that you might have noticed about this problem is that we have a fraction in our b value. Half of 5 is just 5 over 2. If we square 5 over 2, we get 25 over 4. We just square the numerator and square the denominator. Now, before we just subtract 25 over 4 on the outside, we need to multiply that by this negative 16, the stretch that we took out. So that's going to give us negative 16 times 25 over 4. So I'm actually going to write that. So we're subtracting negative 16 over 1 times 25 over 4. And the good news is 16 and 4 are divisible by 4. So this is actually just going to become 4 plus 100. That's not so bad. So g of t is going to be negative 16 times t minus 5 over 2 squared plus 104. So the maximum height is the y value of that vertex. The maximum height is going to be 104 feet. The second question is asking again, when does it hit the ground? So we're going to set the function that we just created equal to 0, and we're going to solve. So the function's equal to 0. We subtract 104. We divide by negative 16. This is going to give us 13 over 2. Then we're going to square root both sides. So that's going to give me the square root of 13 over 2 equals t minus 5 over 2. And plus or minus should be here. So t is going to be 5 plus or minus. I'm going to go ahead and rationalize this denominator. So I'm going to multiply by the square root of 2 over the square root of 2. So this is going to become the square root of 26 over 2. And this should be 5 over 2. And again, the only answer that makes any sense for us to talk about here is the positive answer. So it will take 5 over 2 plus root 26 over 2 seconds to hit the ground. And you could combine that to be one fraction. You could say 5 plus the square root of 26 over 2. That's another way that you could write that. So key ideas in this section. Completing the square is a strategy that allows us to use the square root method when a problem is already written in standard form or just isn't already written in a way that we could solve it using square roots. There are certain circumstances where it's easier to use complete the square than others, which is why we're going to learn how to solve using the quadratic formula in our next video. We can use complete the square to write a function in vertex form, which helps us with word problems and with being able to identify the vertex and graph. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.